Hi, and welcome to this practical demonstration and follow-up calculation for percentage yield and atom economy. So quick knowledge recap of those two things. Firstly, percentage yield is the actual moles made over the theoretical moles that you'd expect to make times 100. This is a measure of the efficiency of the reaction as it actually happens in reality. It's slightly different from atom economy, which is a measure of the efficiency of the reaction in terms of the proportion of reactant atoms which end up in your desired product. So the way you work out atom economy is the molar mass of the desired product divided by the sum of the molar masses of all the products times 100. So we're going to use the reaction of copper carbonate with hydrochloric acid, and we're going to focus on carbon dioxide. It's easy to collect and measure, so we're going to make this our desired product. So you need to work out the molar masses of the individual products and apply the calculation using CO2 as the desired product. So taking all the information about molar masses from the periodic table, you can see where I've got 134.5, 44 and 18.0 from. So that means the atom economy is 44, which is our molar mass of carbon dioxide, divided by the total molar masses of carbon dioxide, CuCl2 and H2O. So that gives us 22.39%, which in fact is not very efficient because there's two other waste products being made, the water and the copper chloride. In order to make the atom economy bigger, all you need to do is find a use for the CuCl2 and the H2O, and you can either sell them or find a use for them in your chemical factory, for example. So the demonstration to find the percentage yield of CO2. Remembering that percentage yield is actual moles of product made divided by theoretical moles of product expected times 100. So to prepare the correct amount of reactants, we use what's called a gas syringe. So that we collect less than this amount, it has a capacity of 100 centimeters cubed. We need to work out how much copper carbonate to start with. Remembering that the reaction vessel itself contains about 20 centimeters cubed of air, we're going to use a test tube as our reaction vessel. That is going to be pushed out at the beginning as the gas is made behind it. So I'm planning to collect about 50 centimeters cubed of pure CO2. So looking at our equation again, the volume of CO2 is 24,000 N if you're doing volume in centimeters cubed. So if we imagine that you've got 50 centimeters cubed you're trying to make, the moles of CO2 is going to be 50 divided by 24,000, which gives you 2.083 times 10 to the minus 3 moles. So because the mole ratio is 1 to 1, I need that same amount of moles of copper carbonate. So converting that to a required mass by multiplying it by the molar mass of 134.5 that we worked out before, that means 0.28 grams is what we need. So what we're going to do is just demonstrate weighing out the copper carbonate. I'm going to try to get as close to 0.28 grams as possible. So you can see obviously it's gone to 0.55 already. So it's a bit more than I wanted, but let's have a look and see how much CO2 this might make. So I'm trying to calculate in theory how much carbon dioxide I get from 0.55 grams of copper carbonate. So I actually now have 4.089 times 10 to the minus 3 moles of copper carbonate. It means I'm expecting to make the same amount of carbon dioxide because again, a 1 to 1 mole ratio. So using my V equals 24,000 N equation one more time, this means 98 centimeters cubed, just about measurable in my 100 centimeter cubed gas syringe. So let's carry out the reaction. So I clamp a gas syringe and there's a rubber tubing and a bung attached. I add my known mass of copper carbonate, so my 0.55 grams. From the weighing boat, and I get as much in there as I can, using the spatula to just pull it out and drag it out gently. Then I'm going to add 25 centimeters cubed of HCl. You can see that in the measuring cylinder. So once the acid goes in, you can see and hear the gas being given off. So I put the bung back on the test tube, and hopefully you can see that the gas syringe has actually started moving. So there's a bit of gas just collected there. So I'm having to shake the reaction. It's slowed down now. So we're going to zoom in, and hopefully you can see that there's still a few bubbles being made of gas where my finger is pointing. Now the problem is that that's not actually pushing the gas syringe any further. The gas syringe has stopped. You can clearly see that. So let's use our results to work out the percentage yield. We collected 22.12 centimeters cubed of gas. So that measurement there was 22.0 centimeters cubed. So that's going to be 24,000 times the number of moles of carbon dioxide, which actually ends up being 9.16 times 10 to the minus 4 moles. So putting that into our percentage yield calculation, so the actual moles goes on the top, and the 4.089 times 10 to the minus 3 we worked out before is the expected moles. So dividing one by the other, you get 22.42%, which is quite low. So there's some possible reasons the yield is so low. The solid, there was a little bit left in the plastic weighing boat, and what that would mean is that I ended up reacting less copper carbonate than I thought originally. There's a lag of about half a second between the gas being made and me managing to replace the bung on the test tube. So some gas escaped which didn't get measured. And at the end I pointed to some copper carbonate still reacting at the bottom of the test tube once the syringe plunger is this thing here, once that stopped moving. So if the gas couldn't build up enough pressure to continue pushing the syringe plunger forwards, it would not have been measured. So there's some imperfections in this method. Okay, hopefully this has been a useful look at one way of demonstrating how to measure and then from the measurements calculate percentage yield. As always, thanks for listening. Until next time, see you soon.